Today's video is going to be focused on doing a two-sample z-test for population proportions. So you guys should have read about that yesterday in your textbook, and you may have even started watching the Khan Academy videos on this topic. But I wanted to put out a video today to show you guys how to do this test. So this question is from the 2015 AP exam. So let's just read through it right now, all right? So it says, a researcher conducted a medical study to investigate whether taking a low-dose aspirin reduces the chance of developing colon cancer. As part of the study, 1,000 adult volunteers were randomly assigned to one of two groups. Half of the volunteers were assigned to the experimental group and took a low-dose aspirin each day, and the other half were assigned to a control group that took a placebo each day. At the end of 6 years, 15 people who took the low-dose aspirin had developed colon cancer, and 26% of people who took the placebo had developed colon cancer. At the significance level, alpha equals 0.05, did the data provide convincing statistical evidence that taking a low-dose aspirin each day would reduce the chance of developing colon cancer among all people similar to the volunteers? Alright, so basically, what are they asking us to run a significance test on? They're asking us to run a significance test to show that the proportion of people who take aspirin every day and develop colon cancer is less than the proportion of people who take a placebo every day and develop colon cancer. In other words, we're testing to see if taking aspirin reduces your risk of getting colon cancer. Alright, so the first thing I need to do if I'm going to get full credit on the AP Stats exam is I need to tell them the procedure that I plan to use when I run this test. And the procedure that I plan to use is a two-sample z-test for population proportions. Okay, a two-sample z-test for population proportions. The second thing I need to do is I need to define my parameters. So let's call PA, let's make that equal to the proportion of all people who take aspirin and develop colon cancer. Alright, and so if PA is equal to the proportion of all people who take aspirin and develop colon cancer, then I'm going to make PL equal to the proportion of, and you guys know what I'm going to say here, the proportion of all people who take a placebo and develop colon cancer. Alright, so it's almost the same language for both. The top one is the proportion of all people who take aspirin every day and develop colon cancer, and PPL is going to be the proportion of all people who take the placebo every day and develop colon cancer. After we've stated our hypotheses and our procedure, we need to check the conditions, right? And we have three conditions. The first one is, did we have random samples? Now, this one, it's not a random sample because it says that the people were volunteers. But if you really think about it, I shouldn't say that. So I'm going to take back what I was going to say, but we can check off that random criteria because it says that we used random assignment when we were setting up our experiment. So if we use random assignment, then I'm going to say stated here, and we are going to check that condition off. Just from the scoring guidelines, I can read it to you. It says, right here, it says, because this is a randomized experiment, the first condition is that the volunteers were randomly assigned to one treatment group or the other. The condition is satisfied because we are told that the volunteers were randomly assigned to take a low dose of aspirin or a placebo. That's right off the scoring guidelines. So I know that I can meet that condition. The second condition is my law of large counts. And that essentially says that, the number of successes and failures in each category needs to be greater than or equal to 10. In other words, the proportion of people who get colon cancer, P1 hat, times the sample size has to be greater than or equal to 10. P1 hat, let's run that back. 1 minus P1 hat times the sample size of N has to be greater than or equal to 10. And then the same thing has to be said for, I'm using P1s and 2s. Geez Louise, this should be an A. This should be an A because this is the aspirin group. And then I'll use PL hat has to be times N has to be greater than or equal to 10. And 1 minus PL hat times N has to be greater than or equal to 10. So this condition is just the number of people in the aspirin group who get cancer has to be greater than or equal to 10. This one then is the number of people in the aspirin group who don't get cancer has to be greater than or equal to 10. And the same thing over here. The top one is the number of people in the placebo group who get cancer has to be greater than or equal to 10. And this is the number of people in the placebo group who don't get cancer has to be greater than or equal to 10. Well, in the aspirin group, 15 people got cancer, so 15 is greater than or equal to 10. Check. If 15 people out of 500 got cancer, then 485 people did not get cancer. That's greater than or equal to 10. Check. In my placebo group, 26 people developed cancer. That's greater than or equal to 10. Check. And 500 minus 26, that should be 474 people. That's greater than or equal to 10. Check. So I've met my first two conditions. My last condition is independence. Independence. You guys know I'm not good at spelling. My independence condition now, again, the independence condition, the 10% condition, so I'll put in here the 10% rule. That used to not be mandatory to state on the exam, but it is now. So in the question, they don't mention anything about how large the population is. You can't physically check that condition, so you say what we always say, which is it is reasonable to assume that 1,000 adults is less than 10% of my population, which is all adults. And then we can check that condition off too. And we've checked our three conditions. Okay? The next step is to state my... what are you doing? The next step is to state my hypotheses. So I have my null hypothesis and I have my alternative hypothesis. The null hypothesis is always the statement of no difference. So we're going to hypothesize that the true proportion of all people who take aspirin and get cancer is equal to the true proportion of all people who take a placebo and get cancer. Meaning you could take aspirin, you could take the placebo, doesn't matter. Your chances of getting cancer are still the same. Now what these scientists are studying is whether or not aspirin lowers your chances of getting cancer. So we're going to say in my alternative hypothesis that the true proportion of people who take aspirin every day and get cancer is less than the true proportion of people who take a placebo every day and get cancer. And they want me to test this at the 5% significance level. Okay? Now look at the arrow. The arrow's pointing to the left. The null hypothesis does not just say that PA is not equal to PPL. We're testing whether PA is less than PL. And so because my arrow is pointing to the left, and I'm testing whether or not taking aspirin lowers your chances of getting cancer. So this is less than this. I'm doing a left tail or lower tail z-test. So any test statistic resulting in me landing over here in this bottom 5% of test statistics on the sampling distribution is going to result in me rejecting H0 and saying, nah, the proportion of people who are taking aspirin and getting cancer is so much lower than the proportion of people taking the placebo and getting cancer that it's just not reasonable to assume that these two proportions are the same, and we're going to reject H0. All right? So in order to find out the critical value that we need to be less than in order to make that conclusion, we are going to use that inverse norm function on our calculator, inverse norm, and this is a lower tail t-test, so I can put that entire 5% in the lower tail. And if you do inverse norm on your calculator and then on your guys' calculators on the computer, you're going to choose the left tail button because we're doing a left tail test. You're going to put 5% in the area under the curve. You're going to make the mean 0 and the standard deviation 1. And you're going to get a critical value of negative 1.64. So I can get rid of this z star now because I know that this critical value is negative 1.64. If I end up with a test statistic any lower than 1.64 standard deviations below the mean, then I know that I can reject H0. Okay? So let's keep pushing here. Now I have to calculate my test statistic. Okay? My test statistic is going to be equal to the sample proportion of people who take aspirin every day minus the sample proportion of people who take the placebo every day and get cancer. Let's fix that. Right? So I'm subtracting these two proportions, and then what I need to put that over is something that looks like this, and this is going to require a little bit of explanation for you guys, which is no problem. Let's do this. Let me fix that plus sign. This is a p hat, 1 minus p hat over n2. Now you'll recall that when we were building confidence intervals, I either put P1 hat over here on the left side and P2 hat over here on the right side. And you might be wondering right now why I only put P hat. Okay? And here is the issue. We know that if we are assuming, when we run these tests, we're always running them assuming that the null hypothesis is true. And then we make our decision based on the evidence that we get from the test according to the fact that this is a true statement. Well, if this is a true statement and the proportion of people who get cancer while taking aspirin every day is equal to the proportion of people who get cancer while taking a placebo every single day, then if these two things are the same, then underneath here, this p hat and this p hat should be the same number. Problem is, I don't know what this number is. I'm trying to estimate the true proportion for each of these guys. I definitely don't know the overall total of people who are going to get cancer. So what I do instead is I pool the data. So actually, I wanted to read you guys a little excerpt out of the textbook if I can find it. So here's what the textbook says. It says, you may be tempted to replace P1 and P2 in the denominator with the corresponding sample proportions P1 hat and P2 hat. Do not do it, and here is why. When they're talking about P1 and P2, they're talking about this guy and this guy right here, and they're corresponding the opposite values. So it says you may be tempted. I read you that. It's a significance test begins by assuming that H0 P1 minus P2 equals 0 is true. In that case, P1 is equal to P2. We call the common value of these two parameters P. Substituting this value in place of both P1 and P2 of the denominator, in the denominator of the test statistic, yields this, what I have written here. They show that. And it says, unfortunately, we don't know the common value of P. To estimate P, we commonly combine or pool the data from the two samples as if they came from one larger sample. This combined sample proportion is P hat is equal to the people who meet the criteria in the first category plus the people who meet the criteria in the second category, all divided by the two sample sizes added together. If you would like to reference the excerpt that I just read for you, it is at the bottom of page 631 and the top of page 632 in your textbook. Essentially, what they're trying to say is because we don't know these true values, instead of replacing P1 hat and P2 hat or PA hat and PPL hat in our case, we can't replace, we can't put those values in the denominator because we're running the test assuming that these two values are the same, but because we don't know if these two values are the same, we don't know what they are. Right? So instead, we're going to pool all the data together and we're going to use that common value in the denominator. So what does that look like? My pooled data is going to look like this. 15 people got cancer in the first group plus 26 people getting cancer in the second group divided by, well, there were 500 people in the first group and 500 people in the second group for a total of 1,000 people. All right, and that is going to turn out, let me do a little math here, it's going to come out to about, here, I'll do it again, I lost my spot, and I don't want to keep you guys waiting too long. 15 plus 26 divided by 1,000, and that is equal to 0.041, okay? And so if I want to fill in this piece right here, 1 minus 0.041, let's make that cleaner. 1 minus 0.041 is equal to 0.959. Okay? So let me set up how I'm going to do my test statistic, and I need to keep this number in mind when I do it. My test statistic Z is going to be equal to the percentage of people who got cancer when taking an aspirin every day, which was 3%, minus the percentage of people who got cancer when they took a placebo every day, which was 0.052. So I have 3% in the one group and 5.2% in the other group. And I'm going to divide this by the square root of, in the first group, I have, remember, we're using common values now, 0.041 times 0.959 divided by 500 people in the first group, plus, now remember, and again, because I pooled the data, the right-hand side of this thing is going to look very similar, times 0.959 over 500, okay? And all of this in the denominator comes out to look like I still have 0.03 minus 0.052 divided by, you plug all that into your calculator and you get 0.0125. Okay? So let's calculate our test statistic now. So 0.03 minus 0.052 is equal to negative 0.022, and I'm going to divide that still by 0.0125, so I'm doing that calculation on my calculator right now. So I have negative 0.022 divided by 0.0125, and I get, now I did this on my phone calculator, so it rounds it to negative 1.76 according to the scoring rubric. Let me pull the scoring rubric back up here. Give me a sec. The scoring rubric has the test statistic rounded actually as negative 1.7542. They actually just round it to negative 1.75. So I'm going to use negative 1.75 instead of negative 1.76 that my phone calculator is giving me. So if I come back here, let me just redraw this distribution for us. Here is my sampling distribution if I were to take the proportion of people who get cancer when they take aspirin every day and subtract it from the proportion of people who get cancer, or subtract from it the proportion of people who get cancer when they take a placebo every day, and I were to do that many times, and I were to plot all the results, okay? We said the lowest 5% of test statistics would be negative 1.64, negative 1.64 standard deviations below average. And it turns out that this test statistic is negative 1.75 standard deviations below the average. Okay? So if I want to get a p-value, right? If I want to find the probability of getting a test statistic this low or lower, I would do normal C, D, F. I need my lower bound is negative 1. Let me fix that. Negative 1E99. My upper bound, remember, if this is the cutoff where negative 1.75 is, I want the area under that curve. So I have negative 1E99. My upper bound is negative 1.75. My mean is 0. My standard deviation is 1. And you should get a p-value of roughly 0.0397. Okay? If you round it differently somewhere else in the question, you might get a slightly different p-value here, but if you use these numbers, then you should get something that looks like this. We were testing at the 5% level. Okay? This p-value says that this will only happen by chance. We will get a test statistic. We will get a test statistic this low or lower purely by chance only 3.97% of the time. So what's more likely? The aspirin actually helped lower people's rate of getting cancer, which is why our test statistic was this low, or aspirin and placebo actually work exactly the same, and we got a test statistic this low purely by chance. Well, because my p-value is less than the 5% level of significance, then that means I do have convincing evidence. I am going to reject H0, that the proportion of people who get cancer when they take aspirin is equal to the proportion of people who get cancer when they take the placebo. And I'm going to say that we have statistically significant evidence at an alpha level of 0.05 that aspirin helps reduce the risk of colon cancer. And that is how it's done, ladies and gentlemen. So I hope that this helps you guys. And that's it for today. And tomorrow I have a little bit of a surprise for you guys. I'm not going to tell you what it is just yet, but I got a little surprise for you for tomorrow, so stay tuned for that. Alright guys, have a good day.